All right, so in this example, I am going to do shear and moment diagrams for the simply supported beam. Given this here, simply supported at A, have a concentrated moment here at B at 15 kilonewton meters, going counterclockwise, and then a triangle or a linearly distributed load between C and D of 4 kilonewtons per meter. And what else here? So here in this one, I'm going to show you handle a concentrated moment and a linearly distributed load, and we're going to find the internal shear and moment diagram. So the first thing you want to do, as with any shear and moment diagram, is to calculate the reactions. Okay, so let's calculate the reactions. The thing you want to do is draw what the reactions are. So we're going to have a vertical reaction here, a y, horizontal a x, and cy vertical there. And let's see, ax is pretty trivial. If you do some of the forces in the horizontal, that's going to be 0. So ax equals 0. That's easy. And then here to find the vertical reaction at C or CY, I'm going to take moments about point A equal to 0 here. And this is the reason I take moments about point A is because it leaves me with one equation, one unknown. And in this case here, I'm going to have, let's see, I have this 15 kilonewton meters plus CY times 3 meters, and then this triangular or this linearly distributed load, which is a triangle, has a resultant here. The squiggly line is a resultant. It's not a replacement for the distributed load, but it's a resultant where the resultant would act. And this is the magnitude of this resultant is the area here of this triangle, which would be 1/2 the base, which is 1 meter, times the height, which is 4 kilonewtons per meter, and that makes this resultant 2 kilonewtons. So I have a 2 kilonewton resultant, and the centroid of a triangle is 1/3 of the base right here from the, if you will, the fat side. Okay, so here this would be 1/3 meter. That's that location right here. So when I go back to my equilibrium equation here, this would be minus 2 kilonewtons the resultant, times the arm from point A, which would be 3.333 meters. Okay, and this is going to be equal to 0. Have one equation, one unknown. I punch it into my calculator, and I should get minus 2.778 kilonewtons. And that negative sign just means that the cy here, the way that I've drawn it, is actually opposite the negative, okay? So, but we're just going to be consistent here in terms of how we do things. And so when I do my sum of the forces in the y now to solve for ay, I say positive upwards equals 0. And I'll have ay plus cy minus the resultant of this, linearly distributed load minus 2 kilonewtons equals 0. And that tells me that cy right here is going to, I'm going to make sure I plug in a negative 2.778. So that means that ay minus 2.778 kilonewtons minus 2 kilonewtons equals 0. Okay, and that means that ay is equal to 4.778 kilonewtons. And the positive indicates that the direction that I've drawn it is correct. Okay, so now I have my reactions, my ay and my cy, and that was pretty easy. That wasn't too bad. But what I want to do now is I want to redraw the beam with only external loads and reactions. So in this case, I have here, oops, let's see here. I have here, let's see, I'm using my straight edge. I want to draw something kind of clean. So here, there's my beam. That looks all right. And then I have here, there was one end a meter away was here, and then about 2 meters away, and then the last distance here. So this was point A here, B, C, and D. And I didn't draw in the supports. I just want to draw everything has been replaced by forces, moments, distributed loads here. So I've got, this linearly distributed load here that was 4 kilonewtons per meter right there. I have a reaction here. Now I'm going to draw this in the correct sense. Before I had CY drawn upwards, and that was negative 2.778. So what that means is that CY is actually 2.778 kilonewtons downwards. And then at A, I have a positive 4.778, which was here, 4.778 kilonewtons. And then at B, I'm going to do something here that really helps me in terms of knowing how to handle my concentrated moment here. At this 15 kilonewton meters that I have, this concentrated moment, it was initially drawn or given this way like this. I'm going to draw it on the left-hand side, or the left side of the node at B, okay, or at that location at point B. So I'm going to draw on the left side right here. Bam, right here. This is 15 kilonewton meters. And this means the same thing as what I drew up there. They just, it's still going counterclockwise. It's still, and it's still at point B. Okay, but what it does, it's going to tell me how to jump with my concentrated moment when I draw the moment diagram. All right, so let's now move on to we calculate the reactions. Now we got all the forces concentrated and the external reactions and the external loading all on my structure. And now I got to draw the internal stuff. Okay, so here, let's, to help you draw this internal thing, I like to, wherever I have a discontinuity, I want to, or an edge, if you will, a discontinuity or an edge, I want to draw a vertical line. So bam, right here, this will be for my shear moment diagrams. And I have here like this, and I have over here like this, and here. So wherever I have like a concentrated load, a discontinuity of some sorts, okay? So here, this first one will represent my shear diagram, this first graph right here. So I'm drawing these lines out, and this will be my shear diagram. And so the shear diagram, it's a story, right? You start from 0 here. You have a concentrated load of 4.778 kilonewtons. So here, let's make sure all these units are going to be in kilonewtons here. So I jump up, bam, make that 4.778 kilonewtons. I follow the arrows, if you will, the story, okay? So here I have this right here. I've got nothing, no other concentrated loads or anything or any other loading that's concentrated forces that's going to influence my shear. So I'm just going to go straight across here. I have a concentrated moment that does not influence my shear diagram. So I'm going to keep going across. Bam, right here. Now I'm here and I have a concentrated load of 2.778 kilonewtons. So I'm going to drop down a distance of 2.778 here, which will leave me at 2 kilonewtons here. This point is 2 kilonewtons, and this difference right here is 2.778 kilonewtons right here. So that was my change, okay, that 2.778 kilonewtons. And then here, because this is linear, okay, or function of x is linear right here, I know that my shear diagram is going to be an antiderivative, if you will, or x squared or something, right? So it's going to be parabolic here. And the question is, my parabola could go either like this, or it could go like this, okay? And one of these two is correct, and the way you know is based on the value of the distributed load. So here, what you know is that the value of the distributed load is a slope of the shear diagram, and here, the value of the distributed load is 4 kilonewtons per meter at that point. So right here, I should have a slope of -4, which will be right here like this. So that means that my bottom curve is is my is the way the parabola should go, like this. Okay, and then down here, the value of the distributed load is 0, so that means I should be horizontal right here. Okay, and so this should be an x squared right here. And the change that occurs, this distance right here, has to be the magnitude of this area, which we found earlier was 1/2 base times height, and this was 1 meter right here, and that is 2 kilonewtons. And so this change is 2 kilonewtons and takes us back to 0. Okay, so there's my shear diagram. And now for the moment diagram, I go over here for the moment diagram. So let's draw the moment diagram here. Bam, got the horizontal line there. And here again, this is my moment. The units are kilonewton meter. right here. I have no moment here, 0, okay? But my shear diagram, if I look at this area right here, this area, this was 1 meter. I have a positive shear. That means that this line right here, the value of my shear is the slope of my moment. So here, right here, this slope should be 4.778 kilonewtons, and it's positive. Okay, so this slope right here at this point is 4.778 kilonewtons. It tells me I'm increasing, and the area right here, this area, is 4.778 kilonewton meters. So this area is a change in moment that I should experience right here for between this right here. So this value goes from 0, and the change in moment is going to be a positive 4.778 kilonewton meter, right? Now, I have a concentrated moment here. And sometimes the thing that really messes people up is, does this, depending on which way the arrow is or which way the moment is rotating, do I jump up? Do I jump down? Okay. Now, I could show you, I can break it down, cut it, show you all what's going on the inside. But what you just need to know is that if you're going left to right and you draw this arrow on the left-hand side, I know this is just a trick I use, right? So I put my arrow on the left-hand side right here of my point right here of this point, and if it's pointing down, that means I should jump down. Okay, so here I'm going to go down 15 kilonewtons, which will take me down to like negative 10.22 kilonewton meters. So that means I'm going to jump all the way down. Whoa, I'm going to jump all the way down over here, and this value right here is negative 10.222. And this delta M is my concentrated moment of 15 kilonewton meters. Right there. That's my delta M. And then I have, again, in this zone right here, I have also, for 2 meters, I have this area, which is going to be, this area right here is 9.556 kilonewton meters. And so that means from this point down here, going to the right, I'm going to jump up this area, 9.556 kilonewton meters. So that's going to take me to some point right here, and that is 0.667. Okay, 0.667 right here. And the slope of this line right here should be the same as the slope of that line because this is a constant shear. Okay, so this should be 4.778 versus 1. Same thing here, 4.778 versus 1 right here. That would be my slope of the moment diagram. And now, lastly, is this last part right here. I have a linearly distributed load. I have a parabolic shear, and then again another antiderivative. So that means I would have a cubic moment diagram whose slope here is positive 2, okay? Positive 2 right here. So the slope here is positive 2, and then the slope down here is 0. And so I know that I'm going to have something that goes like that. And this should be an x cubed function right here. And this value, oh, by the way, this value right here, 10.22 with minus 9.556 right here, the magnitude right here is 0.667 kilonewton meters right here. And so if I did everything correctly and if I go down to 0 here, which it should, let's see, that means this area right here should be, the area of a parabola is 1/3 base times the height, which in this case would be 1/3 times 1 meter times the height of 2 kilonewtons, and that would give me 0.667 kilonewton meters right here. So that means I go back down to 0, and that is my moment diagram. All right, hopefully that was helpful. Let me know if you got any questions or if I did anything wrong, but I think it's going to be all right. All right. Good luck. Talk to you later. Structure free.